Okay, we're going to be looking at this problem that comes up in about a Calculus 2 course using um, the concept of work that involves finding the amount of work done to move water through some sort of shape. In this case, we're looking at a triangular trough. We're given some um, size for this trough, so it's 10 meters long. And then the end of the trough has a shape of an isosceles triangle, which is a total of 6 meters tall and 2 meters wide at the top. For this problem, um, we're assuming that the water is filling up the entire tank, and that there is a 1 meter spout at the top that the water has to go through. We're going to keep the density just of water in terms of rho G. I'm not going to plug in any numbers there because it doesn't matter too much. But we want to find the work done to pump all the water out of the spout. So I think one of the hardest things about this problem is really visualizing what is happening. And there's a few things that we want to do first before we start really setting up anything. First, what I want to do is I want to set up some axes and tell myself where the origin is. We really only care about the y direction, so I'm going to say positive y. Oops. I'm going to say positive y is actually pointing downward, and that the origin is here right at the top of the water. So this is my triangular trough, and it's filled all the way to the top, and then I have my 1 meter spout at the top. You can set up your direction, your positive y direction in either up or down. You can set your origin to be at the bottom of the trough, at the top of the trough, somewhere else in the trough. It just might make things a little bit different, a little bit more complicated in some cases. But I like to set origin at the water level, which is at the top of this trough. All right, so the idea here is that we want the water to pump up to the top and out of the spout. And I think if we're thinking about this from like an engineering perspective or a physics perspective, it is a little bit confusing to think how is the water moving like that. We probably are thinking realistically, well, I would need a hose maybe that I'm going to put in my trough. Then the water's going to drain out the bottom to come out of the hose. But here we're dealing with math magic. So this is an idealized system in some ways. So we're just imagining that the water is moving upward through the trough, as if there's almost an elevator, as if there's like a floor that is increasing and pulling the water up through the trough. So you don't have to worry too much about, well, is the water level decreasing now? Is it going to the bottom and then going back up? We're not dealing with any of that. So what we want to do for problems like this is we want to take slices, and we're going to be taking slices in this direction. That didn't come out as well as I wanted. Sure. We're going to take a slice of our water where it's going to have a certain depth to it. So I'm going to give it some thickness like that. And we're going to call that depth of that, or that little height of that, is dy or delta y. We're going to start with delta y actually. So we're going to say that that little height is dy. So the first thing, well, to think about how to get to find the work done, let's think backwards. So we know that work done is the integral of force over some distance, some sort of displacement of whatever is moving, whatever's a force applied to it. We also know that force, in this case, is going to be mass times gravity. That's the thing that we're fighting against. So when we're doing work, we have to overcome gravity in order to move the water up because otherwise gravity is pulling it down. So now to take one more back step, because we want to know what can we do about the shape of this object and compare it to force, we can think of the fact that density is mass over volume, or then that volume is equal to, or that mass equals rho times V. Now this is good because this gives us a map forward. If I can find the volume of that slice of water, I can find the force acting on it. I can find the work done to move one slice of water, and then I can add up all of my slices through the entire trough that I have in order to find the work done for everything. So first, let's figure out what the volume is. In order to do that, I'm going to look at just a cross section of the front of our trough. The reason why I'm going to do that is because if I wanted to take this slice, I'm going to have a different width of my rectangle depending on how deep I am into the trough. So right now, I'm just going to keep this general. I'm going to say that we are at a depth of y because I had picked the top as 0. So if I'm y down, this is where I am. I know that the length of this, or the base of this triangle here, is 2 meters. I also know that the whole thing is 6 meters. So I'm going to use this fact that we have similar triangles and say that I have this outward bigger triangle that is 6 height to base. But there's also this smaller triangle in here that has some unknown base size. So we want to find what that base size is. But the problem is we don't know at the moment what the height of that triangle is. That is this right here. Well, since I know that this part here is y, and I know that the whole thing is 6, then that means the base of my smaller triangle here, or sorry, the height of my smaller triangle here is going to be 6 minus y, because that's just all that remains. So what I need to know now, and I'm going to clean this up a little bit so I can get rid of some stuff in here. What I need to know now is I need to know what this length is. What is my base? So let's set up our similar triangles. I'm going to say that base over height is going to be the base of the bigger triangle over the height of the bigger triangle. So now I know that my base is going to be 1/3 times 6 minus y. So that gets me the little, I guess if we wanted to say that we have this volume that looks like this, that gets us the length of this rectangle. This is my base right here. We already know that the height of this is delta y. So the last thing we need is the width of that rectangle. That doesn't change no matter how deep I am in my trough. It's always going to be that 10 meters. So I can put a equation together now for my volume based off of how deep I am in my trough. So the volume is going to be our base times our height times our little width, 1/3, 6 minus y times 10 times, and I'm going to keep it as delta y right now. All right, so we have our volume. Now, as I mentioned before, from the volume, we can get mass. And then from mass, we can get force. So we know that force, which is mg, is going to be, and it's going to be rho vg, or rho g. We're going to just keep that together. And I can plug in everything else here. And we're going to say that this is the amount of force needed to just lift up or just move one of those little slabs of water in there. If we wanted to know what is the work done now, so what is the work done just on that slab? Well, it's going to be the force that we're overcoming, or the force that we have to apply to that slab, times the distance that that slab has to go. So let's go back to our original figure with our axes and think about, for a slab of a certain depth here, so for a slab here, how much distance do I have to cover? Well, since it's at a location of y, I'm always going to have to cover y here. But since I also want it to come out of the spout, I need it to also cover that 1 meter. So I'm going to say that this is going to be the force on that slab times y plus 1, because I need to cover both y and 1. If we wanted to do a little bit of a check here to make sure this makes any sense, we could talk about, if I was at the very top of the water, how much distance do I have to cover? So at the very top of my water, I'm only going to be traveling through that 1 meter spout. And sure enough, at the very top of my water, my y value is 0. Because of how I defined the problem. So the distance that's going to have to travel is just the 1 meter. At the very bottom of the spout, or of the trough, we see that we're 6 meters down. So I would expect that the water at the bottom has to travel those 6 meters, and then it has to travel that 1 meter at the top. And how I've defined my axes at the very bottom, this right here is where we have y equals 6. My tablet is not liking me today. So that is where I have y equals 6, and sure enough, if I plug in y equals 6, I will see that the distance this has to travel is 7 meters. So this seems like it's a good check. This seems like it would make sense for what we expect for this sort of problem. So now I only know this is the work done to move 1 slab of water. But I want to move all of the water. So we're going to add up all those slabs. We're going to take our delta y to go infinitesimally small. So we're going to convert it to an integral. And I'll talk about the bounds of this in a moment. But as we said before, this integral is going to be force times distance. This is going to be rho g 1/3, 6 minus y times 10 times y plus 1. And now we have dy. So I want to make sure that I am integrating my bounds correctly. I'm not integrating over the distance that it's traveling. I'm integrating over my slabs of water. So I want to add up all of my water slabs. So that starts at y equals 0. the very top of my water, and goes all the way down to y=6, the very bottom of my water. So in the end, this is the equation that we get for work. And we can clean this up a little bit to make it look nicer if you would like, but this works just as well if we want to just know how to set up this sort of problem. Had we used a different axes, such as origin at the bottom and y up being positive, we would get a slightly different answer, but in the end, it will be of a very similar process and a very similar form. But we would see that the way that we find our volume is going to be a little bit different. And we're also going to see that since we defined y differently, then the distance that it travels is going to be different. But the important thing is that when you integrate, in both cases, no matter what your integral is, you will get the same answer in the end. So the final answer doesn't depend on the coordinate system, but the immediate steps do. So this is just one example of how we can use work to determine how much water is going through our trough, and how to break that up by slices of volume.